Okay, so today we'll continue the chapter on ODE, right? So over the last week, we have basically finished talking about the methods to deal with several different types of first order ODE, right? So and now what's left for this part of the chapter is that we'll talk about a couple examples when none of these methods can be directly applied. Okay, and the strategy is that we will try to use some tricks, some variable change to convert it to looks like one of these forms, and then use the method that we have already learned. Okay, so then that means the trick of using change of variables is well, in many cases, there's not really is a standard recipe to do that, right? So sometimes it really depends on the experience, and you need to make some educated guess. Okay, so let me go to this. All right, so this is an example that requires the so-called change of variable. Okay, before we can use any method that we have learned. Okay, so if you look at this equation, first of all, it might looks a bit similar to one of the problems that we did in last week's tutorial. Okay, so in the tutorial last week, if I have it here. So let me take out the tutorial files from last week. So in question 2, right? So tutorial problem last week. So we have a differential equation looks like this, right? So it's very similar to what I am going to talk about, right? So the form looks like I have a polynomial or a linear function of x and y for the numerator and the denominator. Okay, and remember the trick we used last time. Okay, the trick we used last time was actually also a variable change, right? So we define a new variable x1, okay, which is equals to x plus some constant alpha, right? And then we define a new variable y1, which is equal to y plus some constant beta. And then we converted this equation into the so-called homogeneous equation, right? So if you look at this, okay, so now can we use the same trick? Okay, can we use the same trick? Right. So that means that can we try to define these two new variables? So x1 equals x plus alpha, and y1 equals y plus beta. So that's the first thing that I want to try to see if it works. Okay, so if you actually do that, okay, you'll actually realize very soon that it won't work. Okay, it's because for the numerator, okay, for the numerator, after you do this substitution, you'll find that it becomes this. Okay, and then the denominator, what you'll find is this. Okay, if you actually do this substitution, that's like what we did in the last tutorial. And now you realize that what you there's a mistake here. So what you want, right, just like what we tried to do last time, is what you actually want is that you want this one goes to 0 and this one go to 0, right? So that means you require right, so the alpha and beta satisfies these two equations, okay, and you find that there's just no solution, okay, there's just no solution. But because from the second equation, you find that this alpha minus beta has to be equal to -1. But if you substitute alpha minus beta equals to -1 back to the first equation, then you have this -2 plus 3 equals 0. So that means there's no solution. Okay. So here we'll use another strategy here. So first of all, you can see that the numerator, if we just group the terms, so I'll write it this way. So x minus y, okay, come together, okay, no matter it's in the numerator and the denominator. So then what we try is that we try to let the new variable u, okay, which is equals to x minus y. Okay. So then what happens is that you have du dx, okay, equals 1 minus dy dx, right? And then if you do that, right, so you just replace this dy dx, right, so with this du dx, right, so then at the left hand side, right, because just 1 minus du dx, and then the right hand side, what you also have is only the terms in terms of u. So then this is, now we know how to solve it, right? So because it's du dx, right, so equals to some function of u, okay, and then how do we do that? So basically, this is just the separation of variable, right? So and by that, and then you get the answer. So you could imagine that the similar trick can be applied if you have, whenever you have a function of this form, right? So if you have the numerator, okay, so that has this ax plus by, okay, maybe multiplied by, again, some constant, right? 2, let's say 2, right? Again, plus 3. And then if the denominator is ax plus by plus 1. So then if you have this differential equation, right? So you can use the same trick, right? So this time you just let u equals ax plus by. So then so this is right. So this is just a simple example that by using variable substitution, okay, we convert the differential equation, right? So to a form that we are familiar with, and then solve it. Okay. So another example, okay, so this not just an example, this type of equation actually has a name, which is known as the Bernoulli's equation. But don't be confused, okay, with the Bernoulli's equation that you might have heard in fluid dynamics. Okay, so so this is not that one. Okay, but this is also called the Bernoulli's equation. Okay. So Bernoulli's equation, okay, take this form. Okay, take this form. So first of all, right, so if you don't have this y to the n on the right hand side, right, so you know how to solve it, because then it just becomes a linear ODE, right? So you just use integrating factor, right? And even if we have this y on the right hand side, just y, but not y squared, but not y cubed, you also know how to solve it. right? So because if this is just y, right? So then you can just put this bxy also to the right hand side, right? And then do separation of variables. However, now we are trying to deal with the general case, okay, where n can be not just 0 or 1 here, so it can be 2, 3, 4, right, or even 1/2, okay, 3 divided by 2, okay, any number. Okay. So then the trick is to let a new variable, okay, let u equals y to the power 1 minus n. Okay. So if you do that, okay, so and then if you find the relation between dy dx and du dx, okay, so this is what you got. So then you replace this dy dx by this whole term here, then your ODE becomes this. Okay. So then after that, okay, you also want the y to be all replaced by u, right? So if you also replace all this y by this u, okay, so then what I try to do here is that I multiply both sides, divide both sides by y to the n. Okay, so this is it. And then this one is exactly just u. So then at the end, so from here, after making this variable substitution, okay, so I convert the ODE to this form, right? So this is ODE for u, but this is a linear ODE, right? So for u. And then, of course, if you arrive at this step, then you just use the integrating factor. Right? So example here, right? dw dt plus dw equals a times w to the power 2 divided by 3. Okay. So what do we do? Okay. So actually, okay, maybe for this example, you also can do it by separation of variable, right? Because you can put all the terms with w on one side and just t on the other side. But here, okay, so let's do it using the trick that we just learned. Okay. So right, so what is the trick, right? So whenever we see this, right, so this is w to the power n, right? So then we have this u equals w to the 1 minus n, right? So n is 2 divided by 3, then 1 minus n is 1 divided by 3. So then with this, right, just do the derivative, and then you just convert the equation, right? Just the same procedure as what we had from the last slide, and you realize that you convert the ODE in W, right? So becomes the ODE in U, and then this is of course a linear ODE, and then you just use integrating factor. So then that means, so what kind of variables substitution that we are going to use really depends on really is a case by case consideration. Okay. So there's one more case I want to talk about. Okay, so that one is in this supplemental note actually. So this one, what we are dealing with, okay, so again, is the differential equation of this form. Okay, so we have considered this form, right? So when we talk about the so-called exact equation, right? So remember that this one, right? So can be solved, right? So if m can be written as the partial derivative of v with respect to x, and this n can be written as the partial derivative of v with respect to y, right? So if this is in this form, then this is so-called the exact equation, and we knew how to solve. However, right? So if this is not satisfied, right? So that means if this equation cannot be written as this form, then last time we didn't mention how do we do it. Right? So the strategy here is that suppose, okay, so now suppose this equation, okay, so indeed it's not in this form. Indeed it's not in this form. But we try to multiply a function, which we again call it the integrating factor, okay, such that, okay, so the equation after multiplying this integrating factor can be written in the form of exact differential. So that means after multiplying this, right, so then my dx is with this mu m, right? So and then my dy is with this mu n. So if you can indeed, right, find this integrating factor, this function, right, that can do the job, then that means by definition, there exists a function, right, such that this partial v partial x is given by this, right, and this partial v partial y is given by this. So then of course, if it can work, then what is the solution of this equation? So finding the solution of this equation, right, so would be, so the solution to this original equation would be the same as the solution of this equation, right, because you just multiply some function here, unless this mu that you multiply is a constant zero, right? So otherwise, right, so this equation, the solution is the same as, right, so the solution of this equation here. Okay. So that means now we just focus on solving this equation, right? So instead of this equation here. And now, right, so we, as I said, right, so we want to carefully, right, so multiply this integrating factor such that, right, so this mu m can be written as this partial v partial x, right, and then this mu n can be written as this partial v partial y. So this is our hope, right? So we hope that we can really find this integrating factor, and if it works, then the job is just to find out this v function, right? And that solution to this differential equation, this exact equation, is just v equals constant, right? Just like last time when we learned about the exact differential equation. So, but at this point, we don't know anything about this mu function, right? So we just hope that we can find such a function that can give us this relation. Right? At this point, we don't know anything about mu. So, but what we know is that mu has to satisfy this equation, right? So because again, I hope you still remember, right? So because of the fact that this partial these two derivatives has to be the same, right? So that's why this equation has to be satisfied. So we don't know mu, but we know that mu has to satisfy this differential equation, right? So this is actually a differential equation that involves partial derivatives. So the problem is that solving this equation, okay, to find mu by itself is also not an easy job. Okay, solving this, okay, usually it's not easier than solving the original equation itself. So that means, okay, in practice, okay, so this integrating factor can only be found in special cases. So then there's not a general standard recipe. Okay, so to actually find out this mu. So then we'll just focus on the so-called special case. Okay, is that first? Okay, let's hope that there exists an integrating factor function that only depends on x. Okay, so in general, this integrating factor function of x and y. Okay, but let's say I hope that there exists integrating factor function only depends on x, so that I can just write this mu x. So in this case, of course, this mu still need to satisfy this equation here, right? So however, because of the fact that this mu is just a function of x, okay, so, and if we actually go from this equation, right, so what do we get? Because mu is not a function of y, so the left hand side is just mu partial m partial y, right? And then the right hand side. So what is the right hand side? The right hand side. Okay, so we apply apply a chain rule, right? So what we have is mu partial n partial x plus partial mu partial x times n. But partial mu partial x, well, actually it's just d mu dx, right? Because mu is just a function of one variable, which is x. So then from this, you're changing the subject, use d mu dx as the subject, then you get this equation here. So now, if I want to get mu, okay, I need to solve this differential equation. So again, we ask ourselves the question, is it easy to solve? Okay, we actually don't know. But if, again, we consider special case where if it so happened that partial m partial y minus partial n partial x is just a function of x, and that means this whole term is just a function of x, then we should be able to solve this ODE just by separation of variables. So then in that case, in this special case, we should be able to find this mu of x without much difficulty. So that means the requirement is here, right? So partial m partial y minus partial n partial x has to be the function of x only. So then let's look at this example. Okay. So solve this, right? So first of all, check whether, okay, so I let this component to be capital M and I let this component to be capital N. Okay. First, check whether this is an exact equation. Of course, it's not, otherwise it won't be an example here. But anyway, if you do it, right, so do the partial m partial y and partial n partial x, but you find that they are not equal. So that means this is not an exact equation, right? That's the first thing we know. And then the strategy that we just learned is that we hope to find an integrating factor that would make this whole equation becomes an exact equation. So this equation is just what I derived from the last slide. So I hope to find this mu of x that satisfies this differential equation here. So now partial m, partial y, and partial n, partial x have been calculated already. So you put these two terms here, and oh, that's good. This time, actually, you realize that this whole term here is just a function of x. There's some x and y term, but end up all the y are cancelled out. Okay. So then this d mu dx is just given by 1 divided by x mu. So this is separation variable can be applied, and then you find that in this case, okay, so a possible choice for the integrating factor is simply x. So what does that mean? Again, so think back. That means, right, so this one is not an exact equation, right, but this one will be an exact equation, right? So that's the key. So then let's take a look. So after I've applied this mu, right, so for the equation, and this mu m is this one times x, right? So this mu n is this one times x. So now let me check whether indeed this is an exact equation, right? So you take this component, right? So and then take the partial derivative with respect to y, and then take this component, do the partial derivative with respect to x. You find that they are indeed equal. Okay, so that integrating factor works. It helps us to make this equation becomes an exact. So then that means this mu m can be expressed as some function v that we don't know yet, right? So, but the partial derivative of some function v with respect to x, right? And then this component can be expressed in terms of this partial v, partial y. So then the final job is just to find out v, right? We know that the solution of this equation is v equals constant, right? So then I give you this partial v, partial x, and partial v, partial y, and ask you to find v. Okay, this is not the procedure that I want to repeat again, because I talked about it already. And if you actually try to do that, but you realize that this v is given by this. So, and the solution to the ODE is that this term equals to some constant. So try to digest all the procedures, right? So what did we just do? Okay, we start with this equation, right? M xy dx plus capital N xy dy equals 0. This is what we started with. We found that this is not an exact equation, and then what we try to do is that we multiply this mu to the equation. And hope that, right, so this new equation is an exact equation, right? So, and that, to satisfy that, so that means this component can be written as this partial v, partial x, and this partial v, partial y. And the way that we find mu, right, so is that it has to satisfy, mu has to satisfy this equation. Right? So if mu satisfies this equation, then we know that this new differential equation is an exact equation. If it is an exact equation, then we know that the job is just to find out v, right? And the solution is v equal constant. Okay, so pretty much we have learned all the method for all the method that I want to cover, okay, for the first order differential equation. Okay. So of course, you realize that whenever we solve this differential equation, right? So we always have this so-called this unknown constant, right? So and that constant, right? So comes from the integration procedure, right? So even you apply different methods in solving the ODE, right? So at the end, you always the solution of your ODE always have this one constant C, okay? And that constant C, right? So I think last time I also mentioned is that you have to determine the C by initial condition. Right? So then here I want to clarify, okay, so the difference between the general solution and the solution. Okay, so the general solution has been what we have done last week. So we did the procedure and then we just leave the solution with the C. That is called the general solution. Okay. So and the solution is really means that the C has been determined. Okay, so that means is that is the solution. Okay. But how do we determine C? Right. So and we must provide a so-called initial value, okay, to the problem. Okay. So that means I give you this dy dx equals to some function. Okay. And then I need to also tell you, okay, at the initial value of x naught, okay, what is the value of y? If I give you that so-called initial value, right, so then you can figure out C. And well, so what is the initial value should be? Right? So it really depends on the physical problem that we are dealing with, right? So it's something that we set. We consider the physics problem. Okay. So then that means the solution really means that you have considered the physical situation of the problem already, right? So and then you give the appropriate initial value, and then when you solve the equation, you figure out the C, right? So that means the solution. So then some simple example of the initial values problem. Okay, so I don't need to talk about all of them because, for example, the first one is really the same as what we have done in the last tutorial, right? So the radioactive decay. Okay, so and then also the bacteria growth. These two I'll just skip. Okay. So, but let me talk about the third one. Okay. So this is known as the Newton's empirical law of cooling, okay, or warming. Okay, what does it tell us? So it considered the following situation. Okay, so we have, let's say I have a piece of metal, let's say a piece of hot metal, okay, and then have some temperature T, right? So and then the surrounding is just air, okay, so it's just I call this Tm, and the problem is to find out, okay, so T as a function of time. Okay, so if I have a hot piece of metal here and then it is surrounded by some air, so you not understand that what happens is that T will decrease, right? The metal will cool down, right? So the metal will cool down. And so this so-called Newton's empirical law of cooling tells us that the rate of change of the temperature of this metal or any object, okay, so is proportional to the difference between the temperature of itself and the surrounding temperature, right? So you can see the T minus Tm here. And this K is just a proportionality constant, okay, which is positive. And I have this minus sign in front. So it just means that right? So for example, if I have this T to be hotter than the air, then of course this dt, this D capital T, D time, has to be a negative number, right? Because the temperature is decreasing, or the hot metal temperature is decreasing. So that's why you have this minus sign in front. On the other hand, if you consider another situation, let's say I consider instead of a hot piece of metal, this is a very cold piece of metal. Okay, it's colder than the surrounding air, let's say. Then what happened this time? So this time, of course, you expect that the temperature of this cold metal will increase. And does this equation correctly describe that? Yes, because if you have this T, right, to be smaller than this Tm, then this T minus Tm, of course, is a negative number. And then in front of this negative number, I have another negative sign here. So then this whole term on the right-hand side will be positive. And that's what we expect, right? So this dt has to be positive because temperature is increasing. Okay. So this is an empirical law, so that means it's just from experiment. Okay, so and now so it's not derived from more basic physical law, right? So it's just like from experience or from experiment. Okay. So one thing is that in this case, okay, we have to assume that the surrounding temperature is constant. So Tm is always the same Tm, right? So that means, because you can imagine that if this is a hot piece of metal, if the surrounding air initially is cold, and as the energy, right, so transfer from the metal to the surrounding, so you could imagine that actually the Tm itself will increase a little bit, right? So the surrounding air will be warmed up a little bit, and that would you could imagine that would make the energy transfer, right? So will also slow down, right? So because now this one becomes closer than this one, closer to this one. But here we assume that Tm is constant. Okay, so how do we do that practically? You just imagine that you just keep blowing air, right, through the metal, right? So you keep blowing fresh air to the metal so that the Tm, the surrounding temperature, is always the temperature of the fresh air, which is just a constant. Okay. But anyway, so that's the all the description about the physics, but mathematically, okay, so this is the differential equation that we are going to solve, right? So, and now this equation itself is very straightforward, right? So because all you need to do, right, so it's just a separation of variable. Okay, separation of variable. And now by separation of variable, you just integrate this 1 divided by T minus Tm. Then of course you get this log of function. And now the general solution you get is this, right? The general solution, right? So this is the C is the unknown constant. Right? So this is the general solution. Then the solution that we get is you have to specify the initial condition, right? So in this case, what is the initial condition that we need to specify? Is that at some initial time, I need to tell you the temperature of this piece of metal, right? So at some initial time. So that is the initial condition that we need. Okay. So and here, right? So I give you the initial condition, right? So at T equals T naught, this temperature is equals to this big T naught, right? So then with that, you will be able to figure out this constant, right? E to the C, like this. Then the solution to this problem is this one. So there is no constant C here anymore, but you have T naught, right? So T naught, the initial value. And here, just a little bit to be careful about the absolute sign, right? So when you have this absolute sign, right? So you have to consider two different cases, right? So case one is that I have T naught greater than Tm. So that means the hot metal in air, right? So it's the cooling process. So in that case, right? So this equation, right? So then that means this is just greater than 0, and this is just greater than 0. So that means in this case, I just have T minus Tm equals T naught minus Tm multiply the exponential decay factor. So case two. Case two is that I have this T naught smaller than Tm, so this time cold metal. Right? So then the left hand side and the right hand side, actually this one T minus Tm is actually minus T minus Tm. And then the right hand side would be also minus T naught minus Tm. But because both sides have this minus sign, so at the end, we just cancel the minus sign for the both sides. So so in fact, in this case, okay, in this problem, for both cases, okay, so the final solution, okay, so take the same form. Okay, so this. So does it make sense? Okay, so if I have, let me try to draw pictures, and then we see what's going on physically, right? So if I try to draw this temperature as a function of time, right? So first of all, as t tends to infinity, so this exponential term dies, so then t is just Tm. So then this is the what we call the asymptotic value. So that means no matter whether your initial temperature is hotter or colder than the surrounding air, right? So if you wait long enough, then the temperature of the metal will become the same as the temperature as air, right? So that's reasonable. Okay. So now if we look at what happened initially, right? So let's say for case one, right? So if we have case one where I have T naught greater than Tm, so then at T equals T naught, right? So then T will be here. So this is T naught. So and then I have this exponential decay, right? So that means the curve looks like this. Right. So then for case two, right? So for case two, if I have T naught smaller than Tm, so that means initially temperature is somewhere here. And this time, what you have is a curve like this. So this cooling, this is warming. Okay, so let's take a break here. We'll come back at 12:30. Okay, so just one more physics example. So about this first order ODE, okay, with initial condition, and then I'll still have one or two more remarks to make before we move on to the second order ODE. Okay. So this problem, okay, I'm considering the so-called RC circuit, right? So this RC circuit is that I have a battery, okay, connected to a capacitor and also a resistor, okay, and then with this switch. Okay, so first, what I want to set up is that with this circuit, okay, so initially, okay, so this capacitor, okay, is not charged. So that means the Q, okay, on this capacitor is 0. Okay. So once you close the switch, right? So what happened? So what happened is that the current will flow, right? Flow to the capacitor, right? So over time, right, charges will be accumulated on this capacitor, and then there will be a potential difference developed across these two ends of the capacitor, right? So the voltage difference is given by this Q divided by C, right? So then you could see that as you build up more and more charge, right? So this potential difference getting bigger and bigger, and then eventually the current cannot flow anymore. Okay, so because the voltage of the battery, okay, so it's exactly opposed by the voltage across the capacitor. Okay. So so this is the problem, right? So the initial condition, as I said, is that the Q at t equals 0 is 0. Okay, so and then at t equals 0, I close the switch. So then as the current as this circuit is closed, right? So at any time, the we can set up this equation here, right? So the V of the circuit, right? So will have to be equals to, right? So the potential difference across the capacitor plus the potential difference across the resistor, right? So now what I have is that V equals IR, right? So IR is the potential difference across the resistor, right? And then as I said, right, so the voltage across the capacitor is Q divided by C. And here notice that, okay, by definition, the current is equals to dq dt, right? So and with that, right, so I can replace this I, right, so by this dq dt. Then this is my ODE, right? So for Q, right? So my purpose is to find out this Q as a function of time. Right? So this is a linear ODE, right? So you can solve it using integrating factor. Right? So what is the integrating factor now? Okay, the integrating factor is the e to the integral of this 1 divided by RC. Okay. So after integrating, so the integrating factor, okay, so this is e to the t divided by RC. So I think last time, let me just say one thing here. So last time, I think someone asked me about the notation of this integral. So what does it mean by having an integral with this upper limit without lower limit? Right. So someone asked me about this. So what is the meaning of this integral? So I have this upper limit, but no lower limit. Right. So okay, the meaning is the following. Okay, let me clarify again. Okay, the meaning is the following. Okay, so if I have both upper limit and lower limit, so let's say I write this way. Okay, so then that would be, what would this definite integral be? That would be f of t minus f of t naught. Right. So let's say this capital F is the antiderivative of this small f. Right. So if I have both upper and lower limit specified, so this is the definition. Okay. So when I say that there is no lower limit, so the meaning is that I don't have this second term. Okay. So you just take this first term. Okay. And this is just a way to tell you that I am doing indefinite integral, but I don't add a constant. Right. So remember that when we talk about the integrating factor, right? So after you do the integrating factor, the integrated function is without that constant. Right. So really, this strange notation really means that you are doing indefinite integral, but not putting the integration constant behind it. Okay, that's all it means. Okay, so but anyway, the procedure is standard. Okay, so I have multiplied the both sides of this ODE by this integrating factor R. Then I convert the ODE like this. Right. So then what's next? So next is to integrate both sides again, right? So and that one gives left hand side just Q times E to the T divided by RC, right? And then the right hand side is this. Right, and which is equals to so I just this time I just use D as a constant, right, instead of C, because C here in this problem means the capacitance. So I use D as a constant. Okay, and let me simplify it so that it's just equals to D times C plus another constant D prime. Okay. So now D prime is the unknown constant in this problem, right? So how do we determine D prime? So D prime is determined by the condition that when T is 0, Q is 0. Right. So when T is 0, the left hand side, what is left hand side? At T equals 0. So the left hand side is 0. Right. So the right hand side is V times C plus D prime. So that means D prime is given by minus VC. Right. So and therefore, the Q as a function of T is written in this form. Okay, after I put this D prime equals minus VC. Okay. So then I think now we all have the idea, right? So when you solve the ODE, right, so if you don't have any initial condition, you have this so-called general solution where you have this function always comes with a C, right? So and then in an actual physics problem, right? So we always not just set up the differential equation, right? The differential equation itself, right, is from some physical law, right? It could be this circuit, right? It could be Newton's law, right? So it can be any other physical law, right? So, but to actually solve out the physical problem, right? So not just the solution, not just the general solution of this differential equation, but also after you put the initial condition. Okay, so to figure out the constant C. Okay. So here is a theorem. So I just state it without proof. Okay, for if you are interested in that proof, for example, you can go to this reference here. Okay, so what it says is that if I have this first order linear ODE again in this form, and then I specify the initial condition, okay, and if this P and X are continuous function, okay, in some range of x, then there will exist a unique solution. Okay, so for this initial value problem. And that one, I don't think we have much doubt on this one, because you can see from the previous examples, right? So we always just have a solution, right? So then that's the only solution to the problem. Okay. So that's pretty much all I want to say about the first order ODE. Okay, so these two slides I will just skip. If you're interested, you can take a look. Is that what if I don't have this linear ODE, but in general, okay, any first order ODE. Okay, what about the condition for the existence and uniqueness for that? Okay, so next I will go to the part 2 of this chapter, which is the second order ODE. Okay. So specifically, okay, we will focus mostly on the so-called again, the linear ODE. Okay. Remember, this is the general form for this first order linear ODE, right? So, and then this is the general form for second order linear ODE. Okay. So it's linear, right? If we have this whole expression here to be expressed as what? Expressed as the linear polynomial of y and its derivatives, right? So here is y, but not y squared, but not sine of y, right? So, and then this one is just dy dx, it's not dy dx square, it's not dy dx to the power n, right? So this one also. So that's why this is a linear ODE, right? So, and also because the coefficient function, okay, these coefficient function are just function of x, but not function of y, right? So if here I have a term of y here, then this is a nonlinear ODE. Okay. So, but anyway, so this is the general form for second order linear ODE. Okay, and then we will consider two cases separately. Okay, so the first case is known as the homogeneous ODE, which I have the right-hand side to be 0. So, and the second case that we will also talk about is the known as a non-homogeneous ODE. In that case, the second, this g of x, the right-hand side is non-zero. Okay. So, but I mentioned homogeneous ODE before, right? So in the first part, but at that part, I warned you that there are two types of homogeneous ODEs, right? So remember, recall that in part 1 of this chapter, I say this dy dx equals f of y divided by x is a homogeneous ODE, right? So that's what I told you, right, in last week. But notice that, okay, notice that the homogeneous ODE I'm talking about here, okay, has nothing to do with this. Okay. So remember, why do we call this type of equation a homogeneous ODE? Because I told you that this is a homogeneous function, right? So that's why this type of ODE is called homogeneous ODE. Okay, but in this context that I'm talking about here, okay, that has nothing to do with the homogeneous function. Okay, so from now on, when you talk about the second order linear ODE, okay, so homogeneous means right hand side 0, non-homogeneous means right hand side not 0. So that's it. Okay. So then again, just some general theorem first is that now what we will do next, okay, we'll of course also find the so-called the general solution, okay, and also the solution, right? So remember what I just told you about. The general solution is the solution that with the constant c undetermined, right? The solution is that after you determine the constant c, from the initial condition. So here, if I consider this problem, right? So with this second order linear ODE, and with the initial condition specified, okay. So then, and also all these functions are continuous, then there will be a unique solution. So here you can see that in the second order ODE, I need two initial conditions, okay, instead of one. In the first order ODE, I just need to tell you, okay, at some point x naught, what is the value of y? That's just one, that's known as this one initial condition. Right. So here, or I should say that here the initial condition is specified by two numbers. Okay, I get this one. Okay, I should also say that this one is just one initial condition, but it's specified by two numbers. So in first order ODE, initial condition just specified by just one number. So here is two numbers. So, and that actually makes sense. Right? Just think of again, think of equation of motions. Right? Think of Newton's second law. Okay, in principle, right? So when you solve the Newton's second law, that's give you actually a second order ODE, right? So because it's md squared x dt squared equals to some force function, right? So this is the, well, that's the second order ODE, right? So but to actually solve for the equation of motion, to actually find out the x as a function of t for the particle, right? So you understand that you need to specify two things, not just one. First, you need to specify the initial position, right? So that means at some t equals 0 or t equals t naught, where is it? And then you also need to specify the so-called the initial velocity, right? Also at the same initial time t naught, what is the velocity? Right? So your initial condition require you to give me two numbers, okay, in the second order ODE. So then, right, so physically, right, so we are interested to solve this kind of problem, right? So this theorem is nice, right? So again, it tells us that if you have this well-behaved functions, and then if you specify the initial conditions, then it's guaranteed that, right? So the solutions that you got is so-called the unique solution. So that's the only correct answer. So, but before, of course, solving for the solution to the initial problem, first we want to find the general solution. Right? The general solution, again, as I said, is that is the solution that with the undetermined constant. So we will first talk about the homogeneous linear ODE. Okay, homogeneous case, that means I have the right hand side to be 0, so that's homogeneous. So here I talk about the so-called superposition principle. What is it? So that is, suppose I have find two solutions. Okay, so to this differential equation, okay, this y1 and y2. Okay, so then this c1y1 plus c2y2, or which are known also called the linear combination, the linear combination of this y1 and y2 are also a solution to this problem. Okay, so c1 or c2 are any constant. Okay, so these two constants, okay, at the end will be determined by the initial condition. Okay. So first of all, it seems to be something new to us, is that what do I mean by two solutions, right? So in the first order ODE, so when we solve it, right, so separation of variable or integrating factor, so we just have the one solution. right? So although always come with the constant c, right? So but the form of the solutions, right? So it seems like can just be described by just a function that we got from integration, right? So but here, okay, what do I mean by two solutions? Okay, so I'll clarify that a bit later, but let's say let's accept the fact, okay, accept the fact that this, okay, so suppose, okay, so there are two solutions to this equation. Okay. So let's say one is sine x, the other is sine 2x. Okay, let's say these two the solutions to this equation. Okay. So and this superposition principle tells us that c1 sine x plus c2 sine 2x are also solutions. So this known as the superposition principle is actually easy to prove. Okay, so is that well, I just put y1 into this, right? So and then I got this equation, and then again y2, I also put it in the differential equation. I got this. Okay. And then I just sum the two equations together. Okay, if I sum the two equations together, of course the right hand side is still 0, and then the left hand side is this two terms added together. Okay. Not just summing, actually, just it's actually I multiply the first one by c1 plus I multiply the second one by c2, right? So linear combination. So now if you try to rearrange the terms, okay, so all the terms with the second derivative go first, right? And then the middle two terms just with the term with the first derivative, and then the last two terms are the terms without derivatives. And then you realize that, right? So this whole thing, right, is also 0, and that's why and you look at this form, and this form is actually the same, right? Except that this y becomes this c1 y1 plus c2 y2. Okay. So then this proves that the linear combination of the two solutions is also solution. Okay. And now you may keep asking, right? So if I find three solutions? Can I find three solutions, four solutions, right? So and five solutions, and then do linear combination? Okay, so are they also solutions? So if you can find three solutions, four solutions, you can still use the same proof, right? And you will still tell me that, okay, if I indeed find three solutions, the linear combination of the three solutions are still solutions, like c1 y1 plus c2 y2 plus c3 y3 solution. Right. However, here I tell you that if suppose you find two solutions already, okay, and they are linearly independent functions, okay, then these linear combinations, okay, already cover already represent the general solution to this equation. Okay. So that means I'll explain what linear independent in a second. So that means, okay, even you find out a third solution, okay, that third solution can be expressed in terms of your first two. So that means your third solution is just redundant. So once you find two linearly independent functions as the solutions, right? So then the linear combination of these two linearly independent functions already is already the general solution. Okay, so then okay, what does it mean by the linear independent functions? Okay, so the definition is just this. Okay, it's very simple. Is that y1 and y2, okay, so are linearly independent. Okay, of course, when we talk about whether they are linearly independent, we need to first consider a specific x interval first. Okay. Suppose we consider some x interval, right? So, and if we ask whether these two functions are linearly independent, it's just that we just need to see whether the two functions, okay, are scalar multiple of each other. What does it mean by scalar multiple? That means x and 2x, x and 3x, okay, sine x and 5 sine x. So you just take one of the function and then you multiply it by a constant, then you get the second. That means there's a relation of this scalar multiple. Okay, that's it. That's so simple. And the simplest way to test whether these two functions are linearly independent is just that you just need to take the ratio and to see if it's a simple constant, right? So which is independent of x, right? If I give you 5x and 3x, right, you divide 5x by 3x, you get a 5 divided by 3, which is just a constant, right? So over any point on the x interval, right? If I give you sine 3x and also 3 times sine 3x, right? Again, you take the ratio, you just get a simple 3. So that's this, right? So that's the meaning of a linearly independent function. Okay. So now, okay, so that's enough general discussion here. Okay, so is that now what do we understand, right? So we understand that or at least we know that if I have a second order linear ODE, okay, you'll get two you'll be able to find two linearly independent solutions, right? And the linear combination, okay, of these two solutions will form the general solution of the differential equation. Okay. So now let's actually try to solve something. Okay. So we are talking about homogeneous linear ODE, right? So the case that we are going to consider is after a further simplification. Okay, is that instead of having all these coefficient function in front of each term, I just have this constant coefficient function. Okay, a d square y dx square plus c dy dx plus c times y equals 0. So this is the form of the differential equation that we'll be solving. Okay. So how do we solve this? Okay, so you well you just first look at it, you realize that it is the method that we use in the first order ODE won't work here, right? So and the trick is actually quite simple. Is that first of all we just try. Okay, we just say that okay, the solution should take this form. So that actually, I guess that makes sense to you, right? Because you want to find a function, right? So after taking derivative, it still becomes itself, right? So and then after it takes one more derivative, it also remain to be itself, right? So then you add them together, then there's the possibility that this three term added together is 0. So I guess then this trial solution is not too surprising to you. Okay, so now if I say that okay, so this is the trial solution I'm going to test. Okay, so then the key is that I need to find out the R. What is the value of R such that adding these three terms together is 0. And to do that, okay, so let me just actually substitute this trial solution okay, to the left-hand side of the differential equation. If I just direct substitution. And what you realize is that, of course, for all the three terms, you have this common factor, e to the Rx. Right? Let's put it here. And then you see that, okay, because I take the derivative, so each time I take a derivative, I pull out a factor of R down here. Right? So that's why I have this B of R here, and then I have the A of R squared here. Then so that means if this one is indeed a solution to this equation, then this solution has to satisfy this equation here. Right? And e to the Rx, of course, by itself is not zero. So that means I require this first, all this first term in the bracket is zero. So then what I got is a quadratic equation. Right? So this quadratic equation, of course, we know how to solve it. And we need to solve for R, right? And this is known as the auxiliary equation, or also known as or called the characteristic equation for this ODE. So that means now solving these equations is as simple as just solving this quadratic equation. Okay. So now if we go ahead and try to solve for this, solve for R, right? So that's the formula for the quadratic equation. So this is the formula. So now you can see that I have two roots, right? So I have two roots for this quadratic equation. So then so which root should I take, right? So to put it back here. Both are okay, right? Both are okay. So that means either the first root is the first root put in here is a solution, or the second root put in here is also a solution. So then you can see that, well, I have two solutions, right? It basically come back to what I just told you, right? So a few slides earlier. So indeed, now you can actually see that for second order differential equation, you do have two solutions. Okay, so and the general solution, as I just told you, is the linear combination, right, of the two solutions. And for sure, you can see that the two solutions are linearly independent, right? Because one of the solution is e to the R1x, the other solution is e to the R2x, where R1 is not equal to R2. And if you divide e to the R1x by e to the R2x, of course you don't get a constant, right? Unless, which I'll talk about, unless you have the so-called double root or repeated root. Okay, how do we deal with that? I'll talk about that very soon. Okay, but anyway, now let's consider case by case. Okay, so first, the simplest case I would say is that I find roots, two distinct real roots. Okay, so these are just two real numbers. Then your general solution is C1 e to the R1x plus C2 e to the R2x. Okay. So now the second case is that well, the roots may be complex, right? So not always real roots, right? So right, depends on whether b squared minus 4ac is greater than 0 or not. Right? If it is smaller than 0, then my root. So let me write my root in this form. So the root will be alpha plus I beta or alpha minus I beta, right? This complex conjugate pair. So then the general solution, well, but still, this is my R1 and this is my R2. So then I just still use the same form for the linear combination. Right? But here, if I try to rearrange it a little bit, so what I have, if I just, for this solution here, I can take out one common factor, which is e to the alpha. If I take out one common factor e to the alpha, then what I have left with is some complex exponential function inside. So e to the I beta x and e to the minus I beta x. But this e to the I beta x and e to the minus I beta x can be written as cosine and sine, right? Because of this Euler's formula here. So in this case, okay, so let me just stay with, let me try to avoid the complex notations, okay, here, okay, just stay with this cosine and sine. So then in that case, okay, so the general solution can be written as, right, so this exponential function times some trigonometric function. So, and at the end of the day, right, so this C1, C2, okay, which I write this C1 prime and C2 prime here, okay, so are determined by initial condition. So finally, the third case is the so-called double root or repeated root, right? So I only get this R equals to minus B divided by 2A, right? So that means when I have this B squared minus 4AC equals 0, right? So then I get this repeated root. And now if we just try to write the general solution as a sum of two terms, right? So the first thing you might think is that, okay, then I'll just write C1 e to the Rx plus C2 e to the Rx with the same R. Okay, you can do that, but you realize that this time, right, so the two are the same thing, right? So the two are the linear dependent function. So, and in this case, in fact, so this repeated root gives you this first term. And in this case, but we know that for this second order linear ODE, okay, so there always exists two linearly independent solutions. And the second one, okay, it turns out that is this e to the Rx, the same R, right? So this R is equal to the same R, equal to this R because I just have one value for R. But the second solution I have is actually this exponential function times x. Okay, so now you can see that, of course, this and this are linearly independent, right? Because if you divide this one by this one, then what you got is x, right, which is not a constant. But if you don't have this x term, right, so then the first one and the second, the first solution and the second solution are just linearly dependent, and that won't be a general solution. Okay, but of course you might ask, okay, why this? Why this works? Okay. Of course, the simplest answer that we can have is that because it works. Because if you actually substitute this solution back to the equation, okay, it is a solution. But because it is indeed another solution, then you have to write it here. Okay. So, and of course, I will have a better answer, maybe a bit more satisfying. Okay, but first, let's do a little bit of exercise and verify that this one is indeed a solution of my equation. Okay, let me do a small exercise here to verify that. Right, so this one is a solution to this equation. Okay. So what do I have here? So I will have this y equals x e to the Rx. Right. So then that means this dy dx is given by e to the Rx plus this product rule. Right. So R times x e to the Rx. So take one more time derivative. So d square y dx square is given by some rule, right? So R e to the Rx plus R e dx x e to the Rx. And this the second term here actually this one itself is all y. Right? So this one is actually dy dx, and dy dx we got already here. So that means this is r e to the rx plus r times these two terms, e to the rx plus rx e to the rx. And now this is also given by 2r plus r squared x e to the rx, right? So now I want to put these three terms back to the differential equation, right? So first of all, I know that every single term will have this common factor e to the rx. So let me just write it outside, e to the rx, and then with this big bracket, okay. And then what you find is a 2r plus r squared x plus b 1 plus rx plus cx. So now we arrange the terms. So what I'm going to do is that all the terms with x I group together. All the terms with x I group together. Then what you will find is that this. And then all the remaining terms, okay, I just put it behind. Okay, so now what do we see here? Okay, so this one, r is the root of this ax squared plus bx plus c, right? So then that's why this is exactly 0, right? And what about this? R is minus b divided by 2a. So that's why 2a times r plus b is also 0. So that's why the whole thing is 0. So then this is indeed a solution to this equation, right? And of course, even without the x, it is also a solution. But well, at least that's the first answer on why this one is a solution, because it is. So now you can ask a little bit deeper, is that how do we figure out this? So then here I'll give you a slightly different perspective. Is that how do we solve this equation? Okay, without first assuming that the solution take this form. Okay, without relying on this so-called trial solution. Of course, this is just for your interest. Okay, so the key is that you learn how to solve this equation by this auxiliary equations. That's good enough. Okay, but here just for your interest. So here I can rewrite this equation, okay, as the following. What I'm doing here is that I take the a outside, and then of course in general a is not 0, so then this a just go away, and then I write this, okay, just put all the y out here, and then I call this, okay, a differential operator. Remember I talked about the so-called operator, the gradient operator, something you still remember. This I call this a differential operator. Okay. And then now, okay, so this differential operator actually can be written as a product of two operators. So what it really means? Okay, it really means that when I write it this way, that means I first make this operation, right? So do the operator, okay, make this operator operate on this y first, right? And then I get something, and then I apply this operator in front onto what I get here. Right? So that's really that's the meaning. Okay. So and this R1 and R2, okay, so are actually the roots of this equation. Okay, remember this equation. This is the auxiliary equation. So now, this differential equation is rewritten as this form here, right? In terms of this product of two operators. Now, the next step is that I let u equals to this, right? So I let this whole thing to be u. Okay. A new variable. So then what I see is that, right, this operator operate on u is equal to 0. Right, so this is what I got here. So now if I just look at this, right, without caring about how this u depends on y, so this one itself is a first order ODE for u. The first order ODE for u. And this one you can solve, right? So this one you can solve. U is given by this, right? So this is just the separation of variable. Right. So now I have to take care of this part itself. So now I find u, but that's not enough, right? At the end, I want to find y, right? So I solve for u as a function of x, but then at the end, I want to solve for y as a function of x. So then now I make use of this, right? So this operator operate on y is u. That's what we lack, right? And this u, we figure out already, this u is a function of x, right? So then I need to solve this equation to finally get y as a function of x, right? So this equation again is just a first order ODE, right? So that means we instead of solving this second order ODE, right, all in once, we basically break it down into two steps. So in each step, we solve a first order ODE, right? So that's what's happening here, right? So the ODE that we need to solve is this one, right? And this one, again, from the form, you see that you can use integrating factor. Right? So I just simply write down the answer here. Okay, so you can see that this is the solution for y. So here, this integral, of course, you know how to do, but I leave it here because I want to consider two different cases. So case one is that if R1 is not equals to R2, right? So then this integrating this will just still give you the exponential function, right? And then you'll get to this result. However, right? So the other case, right? So the case of repeated root that we spend a bit time on is the case when you have R1 equals R2. Right? So then in that case, integrating this is not an exponential function. Instead, integrating this is the same as integrating a constant, and that gives you a factor of x. And that's why you get a x factor here. Okay. For the case when I have this repeated root. And you can see that that's why the x comes up here. So this is just for you if you are not satisfied by the fact that I just give you this second solution without explanation. Okay, and that one, okay. I hope it's more clear why we have this factor of x when we have this repeated rule. Nevertheless, if you're happy with this, right, if you are happy with this simple verification, okay, and accept that yes, this is also a solution, then that's why it has to be there. Then that's okay for you too. Okay, so I'll stop here for today. Okay, as I said, I will upload the midterm paper from last year, okay, for your practice. And also, you have a homework due this Saturday, okay, but you won't have a homework due next Saturday. Okay, that's all for today. If you have questions, you can come here to ask.